Today we will discuss about the sorting techniques. Sorting is actually a procedure of organizing the element in the desired sequence. When we will study about these sorting techniques, then we will always consider that the elements are to be arranged in the ascending sequence. So there are various techniques for sorting. To name a few: bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, counting sort, and radix sort. So bubble sort is a procedure which will follow the brute force approach. Similarly, the selection sort will also follow the brute force approach. Insertion sort will follow the brute force approach. Merge sort and quick sort, these are under the scheme divide and conquer. Heap sort is a tree-based sorting technique. And counting and radix sorts are the linear time sorting techniques. These are also said to be the stable sorting techniques. To start with, let us discuss about the bubble sort. Bubble sort is a technique which actually resembles with the when you pour some detergent in a bucket of water, and when you mix the detergent in the water, then the volume, different volume bubbles are formed. Out of these, the bubble having the largest volume comes on the surface first, followed by the smaller volume bubbles. So this technique will also follow the same procedure. Let's say we have some numbers. And we have to sort these numbers. We have 6 numbers. So in the first step, we compare the first two elements. We exchange if previous number is larger than the next one. If previous number is larger than the next one, we will exchange these two numbers. So in this case, 150 is larger than 90. So we will exchange these two. Now we will now compare 150 with 80. So 150 is larger than 80. So we will exchange these two. Then we will compare 150 with 20. 150 is larger than 20. So we will exchange these two. Again, 150 will be compared with 30. 150 is larger than 30. So we will exchange these two. 150 gets compared with 70. 150 is larger, 70 is smaller. So we will exchange these two. And this was our first iteration. And after the first iteration, the largest element is at the appropriate position. If we think that we are arranging the element in the ascending sequence, the largest element should be at the last position. Now we will again do another operation, another iteration. In this, I will compare first and the second element. First element is 90, second is 80. First is larger than the second one, so we will exchange these two. Then 90 gets compared with 20. 90 is larger, 20 is smaller, so we will exchange these two. 90 gets compared with 30. 30 is smaller, 90 is larger, so we will exchange these two. 90 gets compared with 70. 90 is larger, 70 is smaller, we will exchange these two. Now we are not going to compare this 90 with 150. There will be no change after if we perform this operation, because 150 will in any case will be larger than 90. So we stop our comparison one step before. So in this case, the second iteration, second largest element occupies its original position. Now, in the third iteration, we will again do the same. We will compare first and second element. 80 and 20 gets compared. 80 is larger, 20 is smaller. So let us exchange these two. Then in the next step, 80 gets compared with 30. 30 is a small, 80 is larger element. So we will exchange these two. 80 with 70. 70 is here and 80 will be here. Now we do not need to compare 80 with 90. In any case, 80 will be smaller and 90 will be larger. So save one comparison. We are doing one less comparison and we are not comparing this element with the next element. Okay. In this case, 80 occupies its appropriate position. We'll again do another operation, another step, another iteration. 20 gets compared with 30. No exchange because 20 is smaller and 30 is larger. Now 30 gets compared with 70. Again no exchange because 30 is smaller and 70 is larger. So now 70 occupies its appropriate position in the sorted array. Let's do another step in which I compare first and the second element. Again there will be no exchange because 20 is smaller and 30 is larger. Now in this iteration, the position of 30 gets fixed. So now I have the elements 20, 30, 70, 80, 90 and 150. And these are the numbers in the ascending sequence. So what we did in the bubble sort, that we compared the consecutive element, and if the previous number is larger than the next one, so we exchanged these two numbers. In the first iteration, we got the largest element at its appropriate position, it means the last position. In the second iteration, we got the position of the second largest element fixed. Second largest element is fixed at the second last position, and so on and so forth. So what we have done here, we had 6 elements, 1, 2, 3, 4, 5 and 6. The number of elements we have is 6 and we perform 1, 2, 3, 4 and 5 iterations. So if I have n elements, then I will perform n minus 1 iterations. Now let us see how many comparisons took place in the first iteration. I compared first and second element. First comparison. Second and third element, 2 comparisons. Third and fourth element, 3 comparisons. Fourth and fifth element, 4 comparisons. Fifth and sixth element, 5 comparisons. So in the first iteration, if I have n elements, then I perform n minus 1 comparisons. In the second iteration, I performed one less comparison than the previous iteration. So since there were n minus 1 comparison in the first iteration, there will be n minus 2 comparison in the second iteration. In the third iteration, there will be one less comparison, so n minus 3 comparison. In the fourth iteration, one less comparison, so n minus 4 iteration, and so on and so forth. In the last iteration, I need to do only one comparison. Now if I reverse this series, so it can be written as 1 plus 2 plus 3 and so on and so forth up to n minus 1. In this series, if I add n and subtract n, this will make no difference. Now see, this entire quantity means 1 plus 2 plus 3 up to n can be written as summation n. Summation n is what? It is the sum of first n natural numbers, or you can say that this is an arithmetic progression with a common difference 1. So the value of this will be n into n plus 1 by 2 minus n, which is actually equal to n square by 2 plus n by 2 minus n, which can be rewritten as n square by 2 minus n by 2. Now means if I do all the iterations in the bubble sort, the number of comparisons required are n square by 2 minus n by 2. Now let us see if I can save any step in the operation we perform. Let's take this iteration, the fourth iteration. What happened in the fourth iteration, that I compared first and the second element, there was no exchange. Then I compared 30 with 70, no exchange. Then after this, I again performed the fifth iteration. I again compared 20 and 30. So I could have saved this step, because if there are no exchanges in the previous iteration, then surely there will be no exchange in the next iteration. For example, let's take another example. Let's say I have the elements 40, 50, 60 and 70. These are the input elements given to us. And if I compare first and the second element, no exchange. Second and third element, no exchange. Third and fourth element, no exchange. So if I do the next iteration, by considering that the position of 70 is fixed in this iteration, if I do the next iteration, then if I compare first and second element, no exchange. Second and third element, no exchange. So I can stop my operation after the previous iteration, because in the next iteration there is no exchange. So in any step, in any iteration, if there is no exchange, I can stop my comparisons there itself, and the iteration which are, or you can say the subsequent iterations are skipped, or subsequent iterations can be skipped. Now let's say the input elements given to us are these. Now if I compare any two elements in sequence, then there will be no exchange. It means this was the first iteration. I performed the first iteration wherein I have compared first and second element, second and third element, third and fourth element, and so on and so forth, but I could not find any exchange. So in the first iteration itself, I can declare that my elements are sorted. Now if I had to perform only the first iteration, then you can see that the number of comparisons which are actually taking place is n-1. And I do not need to do the subsequent iterations. So I can say that my elements got sorted in n-1 comparisons only. So this actually is our best case. And this actually is our worst case, wherein I had to perform all the iterations. Okay. So the best case complexity is written in omega notation. I can write my complexity as omega n. This is the best case complexity. And the worst case complexity is written in big O notation. Now out of the term n square by 2 minus n by 2, if I suppose n is very large, then n square will be even larger. It means the dominating factor here is n square. With respect to n square, n will be much smaller, or you can say that n square will be much larger than n. So my complexity will be written with respect to the dominating factor, which is n square. So now the best case complexity is omega n, and the worst case complexity is big O n square. So now we will make a practice of writing these complexity in the table. So let's say this is the table of all the complexity. So the bubbles, for the bubble sort, the best case complexity is omega n, and the worst case complexity is big O n square. These are the time complexity, the number of comparisons which are taking place, which according to that I have written the time complexity. Now let us write the space complexity of this. So to find out the space complexity, let us write the algorithm of this. In the bubble sort, let us write the algorithm for the first iteration first, then I'll consider that rest of the iterations are similar to this, and we will write the algorithm for the entire bubble sort. So let's say I'm going to write the bubble sort algorithm. So this is the bubble sort algorithm, wherein we are considering that A element is given, which has, so A array is given, which has n elements. So this is algorithm. So let me write a keyword algorithm before bubble sort, and let us begin this algorithm. So what I said earlier, that I will write the algorithm for the first iteration only. So for writing it for the first iteration, there are n-1 comparison in the first iteration. So let us take a loop and iterate it for n-1 time. So for j equals to 1 to n-1 loop, what we will do, we will compare the consecutive elements. So what will be the consecutive element? Aj and aj plus 1. So if previous number is larger than the next one, we will exchange these two. So I have exchanged aj and aj plus 1 element just because the previous number was larger than the next one. If the previous number is smaller than the next one, we do not need to do anything. But if the previous number is larger than the next one, we will exchange these two. So this is the algorithm for the first iteration. And now you can see that there will be n minus 1 iteration. There will be n minus 1 iteration of the similar kind. So let us take entire this in a loop. Okay. So for this, let's take a loop which will vary from 1 to n minus 1. It means we are repeating these steps, the inner loop, for n minus 1 times. Now there will be some changes inside this inner loop. For example, one of the change will be, yes, we are starting every comparison with the first element. In every iteration, our comparisons are starting from the first element. So this j loop will start from 1. But in the first iteration, we are making n minus 1 comparison. In the second iteration, I am making one less comparison. In the third iteration, I will make even one less comparison than the previous iteration, means the second iteration. So the number of comparisons are reducing with every step or with every iteration. So I am making here n minus I. If the value of I is 1, n minus I will be n minus 1. If the value of I is 2, means we are doing the second iteration, this will be n minus 2. If this is 3, this will be n minus 3. So the whichever iteration we are in, the inner loop will perform one less comparison than the previous one. So this is the algorithm for the bubble sort. Now in this bubble sort algorithm, let us try to find out what are the quantities which are given and what are the quantities we have taken from our side in the algorithm. So the quantities which are given are A and N. These are given. So these will not be counted in the space complexity. But while writing the algorithm, what extra quantities we took from our side is I, J, and if I will implement this exchange algorithm might require a third variable. The process of exchanging two elements can be based on taking one third element, but it can also be done without taking the third element. So let's say that we are taking the third element or third variable. So the extra quantities that you took from your side are 3, I, J, and let's say a third variable T. So space complexity will be encountered because of these three variables. Now, if you see, the number of variables that we are taking will always remain 3, irrespective of the number of the elements in the input. If we have 100 elements, then also the number of variables will be 3. If we have 200 elements, then also it will be 3. If I have 1000 elements, this will also be 3. Again, if I have 1 lakh element, then also it will be 3. So this means that the number of variables are constant, or the number of variables are not changing with the changing input size. So it means the space complexity of this algorithm will be constant. So for this, I can write that the space complexity of this algorithm is θ1. We already discussed that the complexities are written in 3 notations: omega, big O, and theta. Omega represents the best case, big O represents the worst case, and theta notation is used whenever best case and worst case are same, or we have only one case. So here the space complexity will be θ1. Best case, worst case, always be 1. So θ1, not 1, in fact a constant time complexity. To represent the constant time complexity, we use the notation theta.